Hello, I'm Dong-Sub Kim from the University of Texas, Austin. And today I would like to talk about anisotropic excitons, which reveals the local spin chain interactions in the van der Waals antiferromagnet, nickel phosphor 3 sulfide. Typically, we are optics group, so we are always thinking about how to detect the spin information from the material by using the optics. And typically, if you use the optical technique to detect some spin information from your system, people try to use the direct light spin interaction. So typically they measure the difference in their polarization change after the light matter interaction to see the spin information from the system. Also, for a ferromagnet, people typically use the circular dichroism or MOC, the kind of technique. Or for antiferromagnet, people use the linear dichroism, or sometimes they introduce the symmetry information, so they can get a spin information by using the second harmonic generation. They are already very good tools to detect the spin information from your system, but however, typically those techniques are somewhat sophisticated, and also you need to analyze the data after you take the measurement. So for science itself, they are already good, but for device application, it's somewhat not that ideal. But if the spin information can be transduced to another properties in your system, so if you can detect spin information from the other properties, then it can be more practical for spintronic applications. For this purpose, actually, there is a good candidate, which is recently investigated, and that is nickel phosphor 3 sulfide, which is a so-called nickel PS3. This nickel PS3 is the in-plane zigzag antiferromagnet, and have a very high the critical temperature about 155 Kelvin compared to the other van der Waals materials. This material is interesting because they have a transduction, the spin transduction to the other properties of the materials. One of the example is that their phonon modes are coupled with the magnetic properties. So if you take the phonon information, you can get information of the spin chain directions in this material. This is the Raman scattering data, and you can see there are a lot of peaks. But if you look at the specifically second mode of the phonon peak, which is named by P2, you can see that at the high temperature, actually it's just one peak, but as you cool down, they become two peaks. It happened because there are two different vibration modes, A-G and B-G mode. And when they couple with the local magnetic structure, because of their direction, the vibration direction is different, so their coupling react to the differently. So as a result, you can see the two different frequency modes in the Raman. And this is one of the interesting feature of this nickel PS3, because you can get a spin information from the phonon mode. But not only this one, but also you can catch the magnetic properties by using their excitonic properties. It's reported that this nickel PS3 have a very sharp exciton peak a bit far below the band gap. And when you compare the polarization dependent PL spectra with the Raman mode, which react to the magnetic ordering, they have some relations. So by comparing the polarization dependent PL and Raman, people figure out that actually by using the PL itself, you can also get information over the local spin chains in this system. So it's very nice because you can get a spin information through some phonon information or excitonic information in the system. So through this transduction, you can use this material for spintronic devices. But however, there are some limits in the previous studies. First of all, if you want to use this photoluminescence, the photo emission for the spintronic devices, you need to understand this PL very well. Some scientists suggested that this PL comes from the quantum entanglement, but However, so from their theory and their observation, actually they can conclude that the PL's origins. But however, with their theory or observation, it's hard to explain all of the observation related to the PL. Yeah, one of the example is the PL peak in this nickel PS3 is very sharp. Their lightness is less than the 1 millielectron volt. Usually, it doesn't happen in the semiconductor device, the semiconductor systems, but their lightness is broad. But with the pictures, is somewhat hard to explain the origin of the sharp exciton peak. And second, if the PL is related to the magnetic properties, then the PL should disappear around the nil temperature of this nickel PS3. This the upper graph is the susceptibility graph, and their susceptibility disappear around the 155 Kelvin, which is the nil temperature of the nickel PS3. But if you see the PL spectra, PL intensity, actually PL intensity disappear far below the nil temperature. This is about the 70 Kelvin. So yeah, it's also vague to explain. And the last piece of the ambiguity is there is the phonon side band next to the very sharp exciton emission. And this kind of features usually recurs the bound states, but still it's hard. Still there is some ambiguity to explain the coupling between a phonon and this exciton pieces. But not only this one, actually there is one more limit. Actually, this is the very serious limit for spintronics applications. That is, recent papers, recent work actually figure out that the spin change direction in this material is always aligned to the crystalline A-axis following their structures. If the spin direction is only one direction, actually it's really terrible to use this platform for spintronic devices because they only have one state. Yeah, of course, since they are the magnetic material, if you give a external the magnetic field, of course, you can flip the spin directions, but from the observation, it requires the very high magnetic field over 11 Tesla. So it's not that ideal for a spintronic applications now. From this kind of limits from the previous studies, we asked some questions and tried to solve the answers. The first question is that how can exciton be coupled with the local spin chains? Because exciton can give your magnetic property, the magnetic information from in this material. Yeah, of course, someone argued that it's from the quantum entanglement, but since they cannot explain all of the features from the spectra related to PL, our team actually alternatively we suggest some alternative explanation of this PL origin based on a defect bound state. Our collaborator calculated magnetic properties and the excitonic properties based on some general sulfur defect into this nickel PS3. And as a result, we have a wave function based on this defect is actually coupled to the magnetic ordering, and they create this specific direction of the photon emission. So based on this defect bound state, we could explain our observation. Also for the sideband peak, also can be explained by this defect bound state. But however, I would like to say that our work just report inconsistency. We just want to let other people that there is inconsistency between the PL and magnetic properties in this system, and suggested alternative explanation. But actually, still the underlying physics is under debate now. And for our next question. So far, people reported that spin change direction is fixed to the one direction following the crystalline A-axis. But is it really true? Actually, there is a neutron scattering measurement in almost 10 years ago, and authors made the open conclusion that actually the plane can be an easy plane, but they cannot say that the A-axis is the easy axis from the neutron scattering data. So still it's an open question, and also, yeah, even if its previous recent studies shows their magnetic direction is along to the A-axis, they just have a few examples. So yeah, we would like to figure out this problem. So we prepared a lot of samples and take the polarization dependent PL and Raman. And as a result, you can see there are a lot of flake, and I took the 3 representative flake for this polarization measurement. And as you can see, the PL and Raman mode, which coupled to the magnetic ordering, shows the different polarization dependence on each of the flake. So yeah, from this measurement, we actually figure out that in this nickel PS3, there are actually the 3 different spin chains. So it's not always just fixed to the crystalline A-axis. To remove the ambiguity of some changing the crystal A-axis rotation, we also refer to one of the Raman mode, which shows a crystal axis but doesn't have any spin information. And here you can see the 3 flake actually shows the same axis for their crystal axis. And yeah, furthermore, we want to know the more properties of their spin chain directions. So we took some Dummer cycle measurement on this system. It means we hit the sample far above the nil temperature and cool down, and we monitor the PL polar map. And after the many cooling cycles, still we observed that spin chain direction did not yet change actually. But yeah, to get a more intuition about the controlling this spin chain direction, we also prepared this kind of stir shape like some samples. And when we measure the polar map of each of the sites, actually we observed that within the same thickness, we saw the one spin chain direction, but on the different thickness, we saw the spin chain direction actually changed. We don't know the reason, but at least we have a hint that if you want to control the spin chain directions in this nickel PS3, the hint is the thickness of the sample. So yeah, to summarize our work, anisotropic exciton labels the local spin chain direction due to the spin photon transduction in this sample, in this system. And due to this property, we could figure out that actually there are 3 different spin chains in this nickel PS3. Still, we don't know why it happened. So further study is required to control the spin chains. But from our study, we have a hint that it's related to the thickness of the sample. So once someone figure out this problem, then I believe that this nickel PS3 can be a good candidate for spintronic devices through the spin photon transduction. Yeah, this is all I prepare, and I thanks to all of our collaborators, and also for NSF and the MERSEC program at UT Austin for supporting. Yeah, thank you for your attention.
Thank you, Dong. Is there any question? Okay, pretty interesting talk. Thank you very much. We can move to the next.